So in this lesson, we are going to use what we know about bond polarity, and we're going to add in the concept of symmetry with the goal of determining the polarity of the overall molecule. Because it turns out that just because the bond inside of a molecule is polar, just because you have a bond that's in the molecule that's polar, it does not mean that the entire molecule is polar. So we need to do a little bit more work to help us figure out the polarity of a molecule. We're going to go through a couple of generic steps on how to determine the molecular polarity. First of all, we're going to use water, H2O, as an example. The first thing to do is to draw the Lewis structure, which is something I'm going to assume that you have already worked on a bit. So there's our Lewis structure. And when we look at this, we want to look at the electronegativity difference for each bond. So that means we need to know the electronegativity difference here and the electronegativity difference here. When we go to reference table S, we find that the electronegativity for oxygen is 3.4 and for hydrogen is 2.2. So the difference here is, when we subtract, is 1.2 in favor of the oxygen. So what we see here is that in this case, we see the electrons are heading in this direction, right? The oxygen is pulling the electrons away from the hydrogen in both bonds, right? And so we know that this bond in and of itself, falling into this range, that each one of these bonds is a polar covalent, right? Each one of these is a polar covalent bond, okay? And so I'm going to draw this again bigger. So what we are going to see here is that we have what's called a dipole moment, right? And so this arrow that I was showing you up here, where the electrons are being pulled towards the oxygen and away from the hydrogen, we're going to draw that as a special arrow called the dipole moment. Okay, dipole moment is an arrow that points to the more electronegative element. I suppose that says it right there, so that's a bit redundant. Okay, so this bond is pulling electrons towards the oxygen, and this bond is pulling towards the oxygen. So stepping back, we should see that this whole molecule has the electrons spending more of their time only on one end of the molecule, right? So the electrons are spending more time here. So we are going to draw the slightly negative charge there, and then the slightly positive charge on each of the hydrogen ends. So drawing our conclusion, based on the answer to this question, yes, the electrons are spending more of their time around only one end of the molecule. So if we're saying yes, we're going to say yes, that molecule is a polar molecule. And if no, the answer is that it would be nonpolar. Okay, so let's take a look at this process again. This time we're going to look at carbon dioxide as our example. And our Lewis structure for this compound, for CO2, and again, we're not going to go through the steps on how to draw this. I'm going to assume that you've worked out the Lewis structure for CO2. There are unbonded pairs of electrons on both oxygens. Carbon's electronegativity is 2.6, oxygen is 3.2. The END for this is 0.8. Okay. So what we see here is that this END between the carbon and the oxygen means that the electrons are being pulled towards the oxygen because the oxygen is the more electronegative end. And on the other side, the same END means that the electrons are being pulled away from the carbon towards the oxygen. Okay, So what we have here is that we do have polar bonds. Okay. We do see that the electrons are being pulled in opposite directions. However, when you step back and look at the whole thing, are the electrons spending most of their time around only one end of the molecule? And the answer there is no, because the electrons going in this direction are equal and opposite to the electrons going in this direction. So in this case, we do have polar bonds, but because they are equal and opposite, the effect cancels out. Okay? And so the answer here is no. There are equal and opposite electronegative poles. And so the polar bonds within the molecule effectively are canceled out. Okay. And so therefore, CO2 is a nonpolar molecule. So here we have a nonpolar molecule that actually has polar bonds in it. Okay, so this generic process kind of took a sideways turn because of that distribution. Okay, so what are we really saying when we say that the molecule is polar or nonpolar? What are we really saying? Okay. We're going to talk about in terms of electron distribution. A molecule is nonpolar when the electrons are evenly distributed around the molecule in all three dimensions. A molecule is polar when the electrons are unevenly distributed around the molecule in three directions. So polar, nonpolar is really about electron distribution. Okay. So we are going to take a shortcut look on how to know whether a molecule is overall polar or nonpolar. And what you're going to do is, once you have a good Lewis structure to look at, you are going to figure out how many lines of symmetry this picture has. And if we look at water, I can draw only one line of symmetry, right? Imagine that this line is a mirror, and on both sides, the molecule is the same. So this molecule has one line of symmetry. Now, once you draw this line of symmetry, what's really fascinating is you can turn that line of symmetry into the dipole moment, right? And effectively, this is like a vector, if you've ever heard about vectors and you will if you take physics. But the net overall pole of electrons is in this direction. The electrons are going to end up on this oxygen end. And so this end of the molecule is going to be slightly negative, and this end of the molecule is going to be slightly positive. Right? We know that the positive really is being distributed here, but overall, when you step back, this end of the molecule is slightly negative and this end of the molecule is slightly positive. So in this case, we have what we call a polar molecule. One line of symmetry, you have a polar molecule. And that line of symmetry becomes the dipole moment, where you show where the partial charges are. Now CO2, if I draw a line here and I draw a line here, as soon as you get two or more lines of symmetry, that's going to tell you that you have a nonpolar molecule. Okay, so that is the very shortcut how to figure out whether or not a molecule is polar or not polar. It's not very helpful in understanding why that is, but it is a shortcut to help you figure it out. Okay. So here's a couple of examples if we're going to use a line of symmetry approach to figuring out if the molecule is polar or nonpolar. I can draw a line of symmetry here. I can draw a line of symmetry here. Here's a line of symmetry. Here's a line of symmetry. Right? I don't need to draw all of those, but if I have two or more lines of symmetry, I know that this is going to be a nonpolar molecule. Okay. What that means is the electrons are evenly distributed around the entire molecule. The electrons are not piling up on one end versus the other. Let's take a look at this molecule. I can draw a line of symmetry here, but that's the only place I can draw one. right? So one line of symmetry means this is a polar molecule. HF, I can draw, oh, and I forgot to, if you decide that it's a polar molecule, you have to draw the dipole moment. And we are going to make it point towards the nitrogen. You might ask, well, how do I know it's pointing to the nitrogen? Well, it comes down to electronegativities. Nitrogen is a 3.0 electronegativity and hydrogen is a 2.2. So this is more electronegative, and that means that's the end that's going to be slightly negative and the opposite end will be slightly positive. So that's how you can set up those charges. HF, there is only one line of symmetry and it is here. So one line of symmetry, this is polar, which means I have to show my dipole moment. Fluorine is an electronegative value of 4.0, hydrogen is 2.2, right? So 4.0 is the more electronegative end. So that's where I'm going to point my dipole moment. That is my slightly negative end, and the opposite end is my slightly positive end. Cl2, I can draw a line of symmetry here, and I can draw a line of symmetry here. I don't need to find more. I know 2 or more lines of symmetry means this is going to be nonpolar. And that's all you need to do. All right, so what we have done in this lesson is we have taken what we know about Lewis structures and bond polarity, and we are applying it to the whole molecule to figure out whether or not we can classify a molecule as being polar or not. We looked at the shortcut that shows you lines of symmetry. One line of symmetry is going to result in a polar molecule. Once you determine which end of the molecule is more electronegative, that's going to be your negative end, and you draw in a dipole moment. 2 or more lines of symmetry, it's nonpolar. You don't have to draw a dipole moment because there is none. All right, that's it for this lesson. We'll see you back in the classroom.